Rotational equilibrium. So the word equilibrium is not new to you, right? What does equilibrium mean? Like in terms of forces.
Everything is balanced out, there's zero.
In terms of forces, what is equilibrium standing for?
Zero net force.
Zero net force. So equilibrium is of two types. One is rotational equilibrium and the other is translational equilibrium. What you have been dealing with so far was only translational equilibrium, right? So we have translational equilibrium. We were dealing with that earlier, and the condition for that is net force is equal to zero. That's called translational equilibrium. Like the force acting on a car that way, and there's another force acting on the car backward. So the net force is zero. The car is supposed to or
stay in
constant velocity. So if the net force is zero, according to Newton's first law, two things can happen. One, it is at rest and stays at rest. And the other one, it is in motion and it is moving the constant velocity. Make sense? That's Newton's first law, and that is equilibrium, in other words. Right? Net force is equal to zero is your Newton's first law, which says the object is going to stay in the same state of motion. Rotational equilibrium is a different thing where you are talking about torque acting on an object. So you can have torque acting on an object, like the door. If I'm pushing the door halfway, I'm still pushing. Why do I have to apply the torque? Even though I'm not moving the door. Because you fight that one. That is trying to pull back. So that is applying a negative torque when you are applying a positive torque. So if you stay still, you apply a torque, and that's applying a torque, and both are exactly equal, so you stay in the same state of motion.
So rotational equilibrium is net torque equals zero.
Which one again?
Net torque.
Yeah. This one, the net torque is equal to zero. That is called rotational equilibrium. Net torque is equal to zero. So if I apply more torque than what is applied by that one, then I'm going to make it accelerate alpha. Make sense? So there will be an alpha existing. That is, if I'm applying a larger torque than what the door is applying on me. How many forces are acting on the meter stick right now?
2,
4,
2, 3, 4, 5. Which one? Decide.
3.
3. Which ones?
Your fingers.
My finger is pushing it which way? Upward. Gravity is pulling it downward. Now, finger is actually pushing it upward. Sometimes in some conditions, it will be hard to find out which way the force is actually acting. Is it upward, downward, and all that? Confusions. And whenever you have confusions, think what will happen without that support. So as soon as this finger is gone, what is happening in the meter stick?
Falls.
So what is this finger doing?
Holding it up.
That is exactly how you will understand the value of a force. The same way as value of your parents. Your parents are always with you. No, seriously, your parents are always with you and you take it for granted. Oh, they're supposed to be there and they're supposed to keep helping you and all that. You take it for granted. But the day when they are not there, you'll start realizing how important they were. Make sense? Same with friends. So the usefulness of something becomes more important only when you miss that object. Like right now, you're taking for granted the air that you breathe. You're breathing this air. You're not really valuing its importance because you think it's supposed to be there. Wherever I go, it's supposed to be there, right? Now, when will you realize the importance of air? When you don't have it and you're getting suffocated, you don't have, it's like carbon monoxide or carbon dioxide everywhere and you don't have the required oxygen, then you start really suffering and then you realize the importance of clean air. Until then, you won't realize it because it's freely coming in and out. So when do you realize the importance of a force? When you see what's going to happen if that force is not there, right? That's how you decide. Seriously, you have to think about this because I've seen students making mistakes in the direction of the force, and the main reason is because they don't really understand which way the force is really helping in that situation. Question. So, how many forces are acting on this? 3. Which is 3? From the fingers and? Gravity, which is right in the center here. All right? Which acts as center of gravity. Now, little physics magic for you all. What will happen if I don't move my left hand, but I just move my right finger towards my left finger? What will happen to the meter stick?
It'll fall.
Which way?
Left.
Right to the right.
To my right?
You're right.
So I'm going to move. So basically, this is what I'm going to do. I'm going to move this finger.
Yeah.
Yeah. Actually, no, it'll fall the other way.
Which
I
way?
think it's gonna fall to your left.
It's gonna fall to his right. It's gonna fall to
I think it's gonna
It'll fall to your right.
It's going to fall that way, this way. Watch out what's
Are
happening.
you gonna increase the
It's gonna
force?
fly.
I cannot increase anything. Look, I'm not doing
Told
anything.
y'all!
I'm not doing anything. I'm just moving it.
It's gonna fall though, look.
It's
Oh
gonna
wait.
go right to the center.
It's just gonna balance.
It will balance all the way to the center. Finally, it will come right to the center.
Do it again.
So
I can do it with my eyes closed. Watch. I'm closing my eyes. I don't even know where the meter stick is now. So I'm just moving it. And finally, it will come right to the center and it will balance right there. It will come right there. You can keep any object in place. Any object. I can keep this marker instant. I can keep the marker instant off my finger and still do the same thing. You can see what is happening. It will keep doing it till it comes to that spot and it will balance right there. You want to try it out? Go ahead. So you can actually see how it actually works. Now, tell me the reason for all this now. Now you're going to now the physics behind it. Watch. Why?
It's because of rotational equilibrium.
Whether I move my right finger towards my left finger or my left finger towards my right finger, the slipping is taking place right there.
there's more.
Say it again.
I'm just saying there's like more weight. There's more torque like pulling down that right side.
There is more force that this is bearing. Reason, because the perpendicular distance. The perpendicular distance and the weight here is shorter. So the weight is right here. And when you apply a force here, this force times this shorter distance the force is going to be higher. And this is hardly resting it. Can you see it? And so what happens is the friction depends on the normal reaction. So the friction is where in which one? On the right side. That's why it is slipping on the left side. But after some time, the friction becomes kind of equal, and then it starts slipping evenly until it comes right to the center. Right? Okay, so now here, even though I'm applying a force with my right finger, why is it not tipping to the right? Tipping this way. It's because this is trying to apply torque the other way. So right now, it is in what kind of equilibrium? And translational, both. Because this meter stick is not moving at all, right? What if this meter stick is moving like this at a constant velocity? Is it in translational equilibrium?
Yes.
Yes. What if the meter stick is moving like this at a constant velocity? Yes.
Oh yeah.
What if it's moving like that at a constant velocity? Still yes. Only when the meter stick is like accelerating left or right or up or down, then yes, this is not equal to zero, right? That depends on the spinning part of it. So if I'm going to spin this like this in its own place, I mean at a constant velocity, constant angular velocity like that, constant. What is the net torque? Zero. If it's moving at a constant velocity, its net torque is zero. If it is spinning faster and faster and faster, then that is different. Okay? So you understand the idea of rotational equilibrium and the condition for rotational equilibrium is net torque equal to zero, and the condition for translational equilibrium is net force is equal to zero. Now when you say net force is zero, you're talking about forces to the right, forces to the left, forces upward, downward, which means the net x component of all the forces must be zero, and the net y component of the forces also must be equal to zero. Because if you say the resultant force is zero, it won't have an x component or a y component. When you say something is in total equilibrium, then all three conditions are applied. This is applied, and this is applied also. And what is torque? What is the definition of torque? Force times, basic definition of torque. Force times perpendicular distance. From where?
The center of gravity.
The pivot. Where's the pivot here? The pivot.
Your fingers.
This is the pivot? Or this is the pivot? Where's the pivot?
It's the center of gravity.
All right. So when you write this one, net torque equal to 0, you're going to say about the pivot. I'll talk about the pivot up some back. Now, what is to be considered as a pivot? Any point. You can consider any point as a pivot. Okay. You can consider any point as a pivot if you want to study this. So let's dive into this straight away and see how rotational equilibrium problems are actually tackled, because this is the theory behind it. Net torque equal to 0, but then how you apply it into problems is what you need to see more. Okay, so keep those conditions. Let's say we have a ladder, a uniform ladder, and this ladder weighs 40 kilograms. The ladder weighs 40 kilograms, and it is carried by 2 people. And the ladder, the total length of the ladder is 5 meters. 5 meter long ladder, that's a meter. It's a 5 meter long ladder. There's one person standing here, and he is 0.5 meters from this end. And there's another person standing here, and he is 1.5 meters from that end. And they're just standing still. They're just carrying it like this and standing still. So one is standing here, one is standing there. Question: how much force is each one putting? How much is the force of support from each one, right? So now, the first thing you do for any of these problems is draw a diagram right there. Okay? So even if you're given in words, you just frame the diagram like this and put whatever numbers are given to you right there. Next, mark all the forces acting on the ladder. On the ladder. The ladder is the main thing. So, what are the forces?
Person 1. Gravity.
So gravity is the first thing. First, always start with gravity. That's right. Gravity acts right in the middle. And that, how much is gravity? Do you know the value? How much?
9.8.
Yeah, which is? All right. So 40 times 9.8. 392 newtons. That is the weight acting on the ladder. Where? At the center of gravity. Why the center? I mean, what position is the center of gravity at? 2.5. Why? Because it says uniform. The ladder is uniform. I told you that earlier. So which means it should be right in the geometric center. Make sense? So right there. What are the forces acting?
The 2 people.
The 2 people pushing. Which way? Is this pulled down or up? Definitely up. Yes. So F1. And again, as I said, if you don't know which way is F1, just think if he's not holding it, what will happen to the ladder? It's going to fall. So what he's doing is pushing it up with a force. This one is also pushing up with a force, F2. And we need to find out F1 and F2. So,
Wouldn't that be equal if the thing's staying up?
no. So that's what we are trying to solve, and then after that we'll go for tougher problems. Okay, so this is a simpler one. Let's see how to do this. And what are the conditions for total equilibrium? Net x force is 0, net y force is 0, and take it one by one. All problems related to this must be tackled exactly the same way. Take it one by one and seriously do it. Net x force is 0. Is there any x force at all? So forget about that condition, because there's nothing at all. Net y force is 0. Apply the condition. Go from one end all the way to the other end and just list all the forces. Take up positive and down as. So what this one is? So net y forces is equal to 0 because x force is not coming in. A positive F1. Keep going. What is this? A negative 392. And then keep going. A positive F2 over equal to 0. So according to this condition, F1 minus 392 plus F2 is equal to 0. Simplifying this, you end up seeing F1 plus F2 is equal to 392, which everybody knows, right? Yeah, the sum of these two should be equal to this. They're supporting it. Now comes the next condition, which is the torque. The torque condition to be applied very carefully. First, if it's a clockwise torque, it is negative. Counterclockwise torque, take it positive. Okay? Just like how you measure angles. You're measuring angles like this, that's positive. If your angles are going downward, that's a negative angle. Minus theta, plus theta, right? Okay. So you use the same convention because angles, rotation, they're all related. So net torque is equal to 0 about which point? The pivot. Where is the pivot? Any point. You can take this point as a pivot. You can take this point as a pivot. You choose the point. You can take here as a pivot, and here, and here. You can choose here as a pivot. It doesn't have to be on the object. You can choose any way you want. But choosing any point randomly is going to make you do a little extra work. And the best way to choose a point is choose a point such that the maximum number of unknowns are eliminated. How many unknowns are here? 2 unknowns. So you take the pivot either here or here. The choice is yours. Now if you choose a pivot here, in the equation that you're trying to build, you will have F1 and F2. So it becomes a simultaneous equation. Now if I take the pivot here only, then I'm going to get rid of this force completely from the equation. Because if my pivot is this, what's the torque by F1? 0. So choose your pivot appropriately. And the idea is this. Choose the pivot as a point where maximum number of unknowns are eliminated. And you choose it wisely. Okay? In this case, you can choose here or here, absolutely fine. But if you choose a certain spot, now what I normally do is I kind of make it black, dark, so I don't miss that point. Now, why the pivot is kind of indicated very prominently here is because all distances, all perpendicular distances are measured to the pivot from all the forces. So don't miss that. All right, so that is a pivot point. And I'm going to take the torque starting from the left-hand side. I keep looking for all the forces. So as I move from here, F1. What's the torque from F1? 0. Nothing. I keep going. This one is applying a torque. Which way? Don't sit down. Clockwise or counterclockwise? Is it positive or negative? Negative. So you say negative. It's negative not because it is acting downward physically. No, it's because it tends to turn the object clockwise. A very common mistake when students take torque is that they still follow the same convention of like, oh, up, down. No, it's not that way at all. This is downward, and that's why it's negative. No, it's not that way. It is because this force about this point is going to turn it clockwise, and the clockwise is negative. So it is 392 times the perpendicular distance. What's the perpendicular distance from 392 to the pivot point?
2.
This distance, which is 2 meters. And now you go to the next one. This is another force, F2. So now F2 is trying to turn it which way? About this point. Counterclockwise, which is positive. And then you put F2 times, what's the perpendicular distance from F2 to this point? From here to here?
3.
That is 2 and that's 1, yes, 3 meters. And over? 0. Now that equation only has F2, so you can solve for F2. And then plug it here and solve for F1. So 3F2 is equal to 392 times 2. So F2 is equal to
784.
how much?
784.
No,
Divided by 3.
divide by 3.
I'll divide by 3. 261.
261 newtons. If that is 261 newtons, substitute that here and you will find F1 then.
131 meters. So,
How much?
131 meters.
100 and?
31.
So who's actually doing more work? I mean, who's struggling more?
Guy 2.
F2 struggling more. because he's closer to the pivot, closer to the center of gravity, right? He's closer to the center of gravity, so his effort
It's
is
almost
more.
double.
He's putting more, and he's putting less. So if you want to transport like a big cabinet or something like that, and you have another person to help you. So this is a cabinet, a tall cabinet. You want to transport that from one place to another place, and you and another person only. So normally when you have something like that long, you just tip it to the side and then carry it, right? So what you need to do is this: open the cabinet and find out, like, where's the weight distribution? Is it all the weight here? Is the majority of the weight at the bottom, which is normally the case for a cabinet? If the majority of the weight is here, and when you tip it like that, the center of gravity is not in the middle, it's here. So whoever is going to take this end will have to struggle more. Whoever is going to take this end is going to be finding it easy.
Take the front.
Okay, so decide where you want to go. Yeah.
Is that why it's like harder to do push-ups if your hands are really close together? Or is that
Close together or?
yeah? Your hands are close together.
Is
that just because of-
I don't know about
Yeah.
I think what he said is right.
You should demonstrate.
close together and far away. I think that's more of a stability and your muscular issues and all that. But yeah, when where your center of gravity is makes a big difference. Your center of gravity, if it is like, if your center of gravity is way below, then you'll find it very easy. If your center of gravity is way below, and when you want to do push-ups, it will be much easier because less effort on the hands. You understand what I'm saying? So your legs here, and then your body is here, your head is here, you're doing push-ups here. Now, normally center of gravity of the person is somewhere there, so therefore, the effort on your hands is all dependent. Suppose your weight is more on this side, strangely, more on this side. That means your effort will be less because your feet will take most of the weight. Your feet will take most of the weight. Less effort on this side. Yeah, there's a lot of physics even in push-ups and all those things. We'll get there slowly. Do you understand this problem?
Yeah.
And you saw how it is done.
Yes.
Let's go to another problem.
Quarter. Somebody say ankles.
I don't want to hear about your ankles.
Here's another problem. Yeah. Here's the problem. Shh. I've already shown you the problem. This is the problem. Meter stick weighs 100 grams. Meter stick weighs 100 grams. It's uniform meter stick. And I'm supporting it the way I'm supporting it, right? Can you see that?
Yep.
The way I'm supporting it is my thumb is at the far end and my forefinger is on the 6 centimeter mark. Draw the diagram. Draw the diagram for exactly this. My thumb is at the far end of the meter stick and the forefinger is actually at the 6 centimeter mark. And it's 100 grams. So draw the diagram first and mark the forces on it.
You say it's 6 centimeters?
6 centimeters, yes. Now, time to draw the forces. First force is
F1.
Gravity.
gravity. Which one? I'm saying first force as gravity. Why? Because there's a tendency to forget that. Most students will be busy with all the forces, forget the gravity part of it completely. All right, so gravity, how much?
0.991.
0.98 newtons. That is the force of gravity. Now, where are the forces acting other than that? Is there a force here?
There's
Which way?
downward.
Downward. Good. There's a force here downward. Let me call it Ft.
And there's an upward force.
There's an upward force acting here, which is Ff. Okay. So, and you can see why they should be in that manner is because imagine the thumb is not holding it. You can see the meter stick tips that way. So what is the thumb doing is to pull it down. Make sense? And the same way the forefinger. If the forefinger is not supporting there, the whole meter stick is going to fall that way. So the forefinger's job is to push it up. So you decide the directions accordingly. And once you're done with this, apply your conditions one by one. So you do it. Can you do it? And let me see if you're doing it right. And that's a meter stick, so you have the measurements. So Fx is equal to 0. Summation of Fy is equal to 0. And the net torque is equal to 0 about any point. You can choose the points. And work on these three conditions and let me know what you get. Many of you have done it kind of right. Some others didn't get it right, multiple reasons. Now, when you are having centimeters and centimeters over here, you can keep centimeters as it is. There's no harm here because, if you use centimeters throughout, because you're equating it to 0, whether you convert it or don't convert it doesn't make a difference. So I'll show you. Net force in the y direction is 0, so it's minus Ft plus Ff minus 0.98 is equal to 0. So this equation is basically Ff minus Ft is equal to 0.98. Leave it there. Coming to this torque equation, you can take the torque about any point. If you're taking torque about here, let's say you're taking torque about that point, then Ft is going to turn it counterclockwise, so it's positive. Positive Ft times the perpendicular distance, I'm going to take it as 6. You can write it as 0.06, but it doesn't make a difference if you don't, it's fine. So even if you use inches, it's fine here. That is good. Ff doesn't have any torque, so that is nothing. And this one is clockwise, so it is minus 0.98 times 0.98 times that distance, that is 44, equal to 0. And so, you have 6 Ft is equal to 0.98 times 44, so you get Ft is equal to 7.18 newtons. And then substitute that over here, and you'll get the other one, Ff, as 8 point? Now, you can just see this. This meter stick only weighs 0.98 newtons, less than a newton. But the effort that you're putting here and here, look at that. It's pretty strong. The forces that you're applying to kind of hold it like this is much bigger than the weight of the entire thing. So it all depends on where you are mounting stuff. So this can be considered as a diving board. Think of it as a diving board. The diving board is supported here and is supported here too. So if you stand on this side, now your weight is going to be making, so you can see how much effort is going here and here. This is not going to be a big issue for a diving board because it's only like pushing it down, so it is okay. But this is an important thing because wherever the diving board is like held, how is it held? Is it held by bolts? And if it's held by bolts, are those bolts strong enough to hold on there? Is the material strong enough to not rupture? All those things are very important points. All right, so you can see all the stuff going on here. Any questions on this? Yes.
So where did you get the 8.17 from?
Because when you substitute the 7.18 into here, and then you take it that side, it gets added to 0.98. Okay. Yeah.
Not only solve for the magnitude, because
Yeah, these are just the.
Okay.
So if you're getting positive answers here, that means your directions that you assumed they're right. The directions of the forces that you put in are right. That's what your answers tell you. Now, if you get a negative answer somewhere here, to be on the safe side, go back, correct your error, and do it again. That's the best approach. But sometimes, like just flipping the minus signs to plus signs and all that will also be fine. Some cases. But the best thing to do, if it's a more complicated problem, is like go back. You guessed one of the directions wrong. Put it in the right direction and then work it again. Yes.
Why is it 44 and not 0.44?
Because I didn't change it to centimeters to meters. I didn't change because it doesn't make a difference. See, even if I divide this with 100 and divide this with 100 and divide this with 100, it's not going to make a difference to my equation. See over here, what's the difference if I had 0.06 here and 0.44 here? No difference, right? So there are some situations where you don't have to really convert. But if you really want to find out an absolute value for a torque or something, then you have to put the units correctly. You understand? And even here, 100 grams, I could have kept the 100 grams as it is, just like that. But then it won't give you the answers in newtons. That's the reason why I did this. Okay? Now let's look at this case. That's a wall, obviously, and that's a floor. That's a smooth wall, like this. It's a smooth wall, and we are placing a ladder on the smooth wall.
Oh God.
Please don't say it's falling. Wait.
No, why? I mean, I can tell you there's no grip over there.
There's the wall.
Ladder 9 meters away.
It's just like this. Look, this is the wall. That's the ladder, and it's resting here. Make sense?
Yes.
That's exactly the picture. Now, the ladder.
The way it should be.
The ladder weighs 50 kilograms. And the length of the ladder is unknown. The length of the ladder is unknown. The ladder weighs 50 kilograms and the length of the ladder is L. And the angle at which the ladder is placed is 65 degrees to the ground. It's a little too small. Should be higher normally. All right, let's say 65 degrees. Pay attention. So the question is this: find all the forces acting on the ladder. Find all the forces acting on the ladder. Okay. So the first thing you should do is yes, gravity. Take care of that first. How much is this force? So that is your gravitational force. That's done. What else is acting on the ladder?
No reaction on the floor.
Where is it?
At the base.
At the base. There is a force upward or downward.
Upward.
Why?
Because you take away.
Because if the floor suddenly gives way, the ladder is going to sink. So what is the floor doing? Holding it up. So let's call it V for vertical. Yeah, what else?
The wall is pushing away.
This wall is pushing which way?
To the right.
To the right. So the wall is pushing the ladder to the right. Let me call it H for horizontal.
Or not vertical.
Now again, why is it this way, not this way? Because if the wall suddenly goes away, the ladder is going to fall inward. So the wall is actually pushing it and not letting it fall. What else?
Friction.
Friction. Where?
The floor.
And the floor. Which way?
Left.
Left or right?
Left.
Left.
So think opposite. Think again. If the friction is not there, what will happen to the ladder?
Slide.
It'll slide and go that way. So what is friction doing is not letting it slip that way, and there is friction. So this is what your job is supposed to be. First thing is like find out where the forces are acting. So we found out there is a normal force here, there is a force here, there is friction here, there is a weight here, and that's it. Now if somebody's standing on the ladder doing a paint job, then you got to consider his weight as well. Okay? So if somebody's standing here, then you have to consider his weight also as part of the problem. Okay, otherwise, if it is just the ladder alone, then that's it now. Let's find all these forces. How are you going to find all the forces? Conditions one by one. Net X force is equal to 0. Are there X forces here?
Yes.
Yes. So start from one end of the ladder, go to the other end, and count all the x forces. What is that considered as? Plus h, right? And this is not x, and that is not x, and this is negative f equal to 0. That only tells you that h is equal to f. You cannot solve it from there. So leave it there. Go to the next condition. Net y forces is equal to 0. Alright? Y forces. There's nothing here. There's a y force. This one?
That's a Y.
Which way?
Negative 490.
A negative 490 newtons. Then I'm not putting newtons and all that as part of the equation. And then
Positive V.
positive v equal to 0. Nothing else. So what does that tell you? That v is?
490.
So we solve for v, but that's not the end of it. We still have to find the other ones. Now comes the torque. Net torque is equal to 0. Where is the best place to take torque? Which way?
On the crown.
On- On the base, yes. Take torque about here. The reason why we are taking torque about there is from our equation, v and f go missing. From the equation, you will not have v or f because they're both passing through that point. So advantage of taking torque over here is we will have only h in our equation. Okay, let's go. About base. You always should write down, like where you're taking the torque. Because if you don't write this, then all the distances, nobody will know from where you're measuring the distances. So if you're putting a wrong distance, I can't figure out, like, where did you actually measure it from? Did you measure from here or from there or where? Torque equal to 0 about any point, but in this case about the base. Now gradually do it. Start from this side, start from here. What's the torque by V about this point?
0.
F about this point? Out. This one. First of all, decide, is it clockwise or counterclockwise? Counter, so positive. So see, force is acting downward, but you're taking it as positive because this is going to turn it this way. So it's a positive 490 times. Where is the perpendicular distance?
We don't have the length.
You need the
L over 2.
L over. What is perpendicular distance by definition?
From the center.
I think I must have asked you to write it down. What is perpendicular distance by definition? What is the perpendicular distance? The moment, where you got introduced to torque, I must have written it there.
It's from the pivot.
It's from the pivot. Anyway, if you're not written it down anywhere, write it right here.
Line of action.
Yeah, say that again.
Line of action of force that
And the pivot.
Yeah.
Shortest distance from the line of action of the force and the pivot. That is your perpendicular distance. Write it down. The shortest distance from the line of action of the force and the pivot. That is your perpendicular distance. Now, line of action means what? So where's the line of action of this force?
straight down.
That's the line of action of this force. What's the shortest distance from this meter stick to that pivot?
The bottom one.
That one. That's how you find the perpendicular distance. Get it? So perpendicular distance is the shortest distance from the line of action, not from the force, from the line of action of the force to the pivot. So don't measure from here to here. That is not perpendicular distance. You keep this and say, all right, this is the line of action, so that is how far it is. So this is the line of action of the force, and this is the length that you are looking to find out. And you know this is L over 2. So if you know this is L over 2 and this is 65, what is this?
L over 2 cosine 65.
Good. L over 2 cosine 65, that's what's going to come in. So L over 2 cosine 65. Good. So far good. So that part is over. Now let's keep going, searching for the next force. There's another force. Is this trying to turn it clockwise or counterclockwise? So it is Negative times h times. Now comes the perpendicular distance.
L.
Again, perpendicular distance is what? It's the shortest distance from the
Line of action.
line of action of the force to the pivot. Where is the pivot? Here. Where's the line of action? There. What's the shortest distance? Where's the shortest distance between the meter stick and this point?
From perpendicular.
That one. That's what you need to find out. Isn't this the same as this?
Yes.
Yeah.
So go ahead and find that. So the line of action of this force, the line of action of that force, so this is your perpendicular distance, which is the same as this. And how much is that? L sine 65. Because this whole thing is L, and that is 65, and this is the opposite side. Okay? So put L sine 65 over equal to 0. Now simplify it. So you have 490 times L over 2 cosine 65 equals to H times L sine 65. Now if you divide both sides by L, L's are knocked out. So L is not coming in the picture now. See, L is gone. The only thing you have in that equation is H. Find out. Plug it in. Calculator. Where's your calculator? Punch it. What is that you get?
114.
How much?
114.
140?
Degrees.
Make sure it's in degrees, yes. So 114. Make sure everybody's getting it right. Is it 114 H? Good. So the push from the wall is only 114 newtons. And if that is 114, what is this? Friction. Yep. Friction is also 114. And you already solved for V, which is 490. So you solve for all the unknowns. Get it? Get it? Just work this equation and you get the answer. Once you have this answer, because H and F are equal.
So is it 2 cosine 65?
No, the 2 cancels.
Oh, that's it.
Oh, never mind.
It's 2.5. I don't think we've yet solved for that state.
We lose her here.
Oh, yes, of course. The energy is. Now, if you do that as an acronym.
Now, when you have an extended object like this, that's when you are looking for a rotation. It's not going to be, rotation is going to be not going to be always there. You have done problems where there's no rotation at all, but you have to apply these 2 conditions. You have to apply those 2 conditions. I'll show you an example of that. So this is a cable, and that is a cable, and that is a cable, and this mass is hanging there. Find the forces in the cables. Now this is also a situation of equilibrium. But there's no question of rotation here, right? Where's the rotation going to come in? There are forces here. Look, there is a tension here, which you don't know. There's a tension here, which you don't know. Well, there's a tension in this rope, which you kind of know. Because what is the weight acting downward? 98 newtons. If that's 98, what's the tension upward here? 98. That means what is the pull downward from this side? 98. Right? So we know this tension is 98 newtons. So basically, this is a problem where this knot is kept in translational equilibrium. The knot is kept in translational equilibrium because there are forces acting And you know why it is not causing any rotations? Because these forces are concurrent. Concurrent forces. Concurrent forces means forces that are all pointing to the same spot. This force, see the line of action of all the forces are right to the same spot, so that won't cause any rotation. If there are concurrent forces, no rotation is possible. Say right now, how many forces are acting on the meter stick? 2 forces. One, I'm pulling it up, and the other one, the gravity is pulling it down, and they're both acting at the same center of gravity. And so it doesn't cause any rotation. This doesn't cause any rotation. But if my force is somewhere else, and this is somewhere else, then it causes rotation. Okay? So in this case, this is a situation where you have translational equilibrium, and no question of rotation at all, because they're all concurrent forces. So you do the same thing. Net x force is equal to 0, net y force is equal to 0, and so on. So let's do the x force first. How many x forces do you see?
One.
Two.
This one. And now you got to resolve it. So you resolve T2 into 2 components. What is this component? This is 60 degrees. So this is 60 degrees. What is this?
T2 cosine 60.
Good. And that means this will be T2 sine 60. So that is your first job. And now you can just go ahead with that fact, x is equal to 0. This is going to be next minus T2 cosine 60. And that's going to be positive 1. So this positive T1, that's it, equal to 0. See, this is negative, that's positive, equal to 0. And the next condition is y. Net y force must be 0. So you apply the same way. That is T2 sine 60 minus 98 equal to 0. So you get T2 from here, and then plug it there and get T1. So you get the solutions for both.
I got 115.
How much?
113.
113?
Yes.
And plug this over here and get the other one.
I'm positive T1 is 107.6.
No, it's 56.
I got 56.5. 56.8.
56. Just plug this in. Plug this here. Cosine, check your calculator if it's in the degree mode or radian mode.
It isn't rating. Yeah.
It is in radian. It should be in degrees.
56.5.
Now think of this situation now. Look at this. Look at me holding the book. Or think it is a dumbbell. Alright. I'm holding the dumbbells or something like that here. Is this in equilibrium?
Yes.
Yes. Where are the forces?
The dragging force there are.
Okay, the book's weight is acting here. Where else?
You're holding it up.
Where am I holding it up?
Fingers.
Where's the fulcrum? Where's the pivot?
Your elbow.
My elbow. So this is a picture. This is a picture. My elbow, my arm, the book,
Oh, that's the your muscle.
biceps.
Yeah,
It's connected here.